welcome to the deep dive. You asked us to explore the fascinating world of sound, to really get under the hood and understand its fundamental properties and, how it plays out in the real world. That's exactly what we're setting our sights on today.
Yeah, and we've got a really comprehensive chapter on sound to guide us. It takes us from the absolute basics of sound as a wave all the way through to the subtleties of how we actually perceive it.
Right. So our mission today is to pull out the most valuable insights from this material, make those complex ideas hopefully crystal clear, and really highlight those aha moments.
Those moments that make you think, wow, I never quite thought of sound that way before.
Exactly. Okay, so where do we begin? How do we start unpacking this sonic universe?
Well, let's dive straight into the heart of it. The nature of sound waves themselves. Our source points out, and this is fundamental, that sound is born from vibrations. And crucially, it can't travel through nothing. It needs a medium.
A medium, right? So like a solid, a liquid, or a gas.
Exactly. Solid like the ground, liquid like water, or gas like the air all around us.
And in air, which is, what we mostly experience, these vibrations move as longitudinal waves.
Longitudinal waves.
Like I picture a slinky, kind of, you push one end and that compression travels down.
That's a great analogy. It travels as these areas where the air molecules are squeezed together, compressions, and then areas where they're spread apart, rarefactions. It's that pattern moving through the air.
Okay. And the speed it moves at, that's not always the same, is it?
No, not at all. It's dictated by the properties of the medium itself. Things like how dense it is and how elastic it is, how quickly it springs back. The source even notes that for gases like air, temperature, and humidity can tweak the speed a bit.
Temperature and humidity, okay. But not pressure, surprisingly.
Yeah, the overall pressure doesn't really have a significant effect on the speed itself, which is kind of interesting.
Now, our ears, they're quite selective, aren't they? We don't hear all vibrations.
Not by a long shot. We're tuned into a specific range, roughly 20 hertz on the low end, up to about 20,000 hertz or 20 kilohertz on the high end.
That's our audible sweet spot. And that range shrinks a bit as we get older, right?
Yeah.
Especially the high frequencies.
That's generally true, yeah. The upper limit tends to decrease with age. But what's really fascinating is the whole spectrum of sound beyond what we can hear. You've got ultrasonic waves soaring above 20,000 hertz.
Like bats use.
Exactly, like bats and dolphins. And then you have infrasonic waves rumbling below 20 hertz. Things like earthquakes or volcanic eruptions can generate those.
And even though we can't hear them, they still follow the same basic rules. They still travel through things at a certain speed.
Absolutely. The physics is the same. They just fall outside our ear's detection range.
Okay. And like any wave, sound waves have these key characteristics. Amplitude.
Which we perceive as loudness.
Time period. The duration of one vibration.
Right. And frequency, which is how many vibrations happen each second, measured in hertz.
And wavelength, the sort of physical distance of one wave cycle.
Precisely. And these are all interconnected. They're not independent.
How so?
Well, the source gives us a couple of really fundamental relationships. First, the speed of the wave, let's call it v, is equal to the frequency, f, multiplied by the wavelength.
V equals F lambda.
Okay. Think of it like this. If waves are passing you at a certain speed and the crests are closer together, shorter wavelength, then more crests must pass you each second, right? So higher frequency.
Got it. Makes sense. And the other relationship?
It's simpler. Frequency f is just the inverse of the time period, t. So f equals 1t.
Meaning if each vibration takes less time, the frequency is higher.
Exactly. The quicker the vibration, the more vibrations per second.
Okay, so we've got a handle on how sound travels as a wave. Now, what happens when it hits something, a barrier?
Ah, that's where reflection comes in. Just like light bouncing off a mirror, sound waves reflect when they strike a surface, especially a hard one.
And it follows the same rules as light reflection. Angle of incidence equals angle of reflection.
Pretty much, yeah. The basic laws of reflection apply.
Does the surface need to be perfectly smooth, like a mirror?
Not necessarily. The source points out that reflection happens from pretty much any surface, smooth or rough, as long as the surface is, significantly larger than the wavelength of the sound hitting it.
Right, that makes sense. And this reflection principle, it's used in some everyday things, isn't it?
Absolutely. Think about a megaphone.
Yeah, the cone shape.
That cone shape is designed specifically to reflect the sound waves forward, concentrating them in one direction instead of letting them spread out everywhere. Makes your voice carry further.
Or those curved shells behind the stage in some concert halls?
Soundboards, exactly. They are carefully shaped and angled to reflect the sound from the performers out towards the audience, ensuring everyone gets a clear, balanced sound.
And even just cupping your hand behind your ear.
That's a simple example, too. You're creating a small reflector to collect more sound waves and direct them into your ear canal. A bit like an old-fashioned ear trumpet.
Huh, okay. So, reflection is key. Now let's zoom in on echoes, that distinct repetition of a sound. What's the physics there?
An echo, as our source defines it, is specifically that reflected sound that reaches your ears after a noticeable delay. So you perceive it as a separate event from the original sound you made or heard.
A noticeable delay. So timing is the crucial factor.
Timing is absolutely everything for an echo. Our hearing system has this thing called persistence of hearing.
Persistence of hearing.
Okay, it means the sensation of a sound lingers in our brain for a tiny fraction of a second, about zero point 0.1 seconds, even after the sound source stops.
Right, like the after image for vision.
Sort of, yeah. So to hear a distinct echo, that reflected sound wave has to take at least 0.1 seconds longer to reach your ear than the original sound did. Or rather, it needs to arrive 0.1 seconds after the original sound has stopped.
So your brain needs that little gap, that 0.1 second silence almost, to separate the original from the reflection.
Exactly. If the reflection comes back faster than that, it just kind of blends in, maybe makes the original sound seem a bit richer or fuller, but not like a distinct echo.
Okay, that makes perfect sense. And given the speed of sound in air, what is it, roughly 340 meters per second?
Around that, yeah. It varies a bit with temperature, but 340 meters is a good average.
So if you need a zero point 0.1 second delay for the round trip.
Right. The sound has to travel to the reflecting surface and back, so the total distance is twice the distance to the surface. Let's call it d.
Okay, so taken equals speed times time, v times t.
Precisely. So second to the 340 meters, 0.1 Liz key, that gives Tekken equals 34 meters.
Meaning the distance d to the reflecting surface has to be half of that, so 17 meters minimum.
Exactly. In air, you generally need a cliff face or a large building wall to be at least 17 meters away to get a clear, distinct echo.
Wow. And that distance would change if sound travels faster or slower, right? Like underwater.
Absolutely. Sound travels much faster in water, maybe around 1,400 or 1,500 meters per second.
So if v is much bigger in the equation, d must also be much bigger for the same 0.1 second delay.
You got it. If we redo the calculation with, say, 1,400 meters for seawater, that minimum distance for an echo jumps to about 70 meters. Much further.
That's fascinating. Really puts underwater acoustics into perspective. Now, what if sound bounces off lots of surfaces, like in a big, empty room? The source calls that reverberation.
Yes, reverberation is different from a distinct echo. It's more like a dense mesh of reflections arriving very close together in time.
So not one clear repetition, but a sort of lingering of the sound.
Exactly. Think of clapping your hands in a large church or an empty gymnasium. The sound doesn't just stop, it sort of hangs in the air and gradually fades. That's reverberation, multiple reflections from walls, floor, ceiling, all blending together.
Okay, so echoes are distinct. Reverberation is more of a wash. Now, the fact that echoes have this measurable delay, that seems useful for measuring things.
Hugely useful. It's the basis for the echo method of finding the speed of sound, for instance.
How does that work?
It's pretty straightforward, actually. You need a known distance, d, to a good reflecting surface. Then you make a sharp sound like clapping two boards together, and you precisely measure the time, t, it takes for the echo to return.
And then you use that v equal 2dt formula we just talked about.
Exactly. You know, d, you measure t, you calculate v, the speed of sound in that specific environment.
Clever.
Yeah.
And this basic idea of sending out sound and listening for the bounce back that's behind sonar and things like that.
Absolutely. Sound ranging is the general term. Using sound emission and echo detection to find stuff. Animals perfected it long before we did. Bats navigating in the dark, dolphins hunting. They use ultrasonic clicks.
Echolocation, right. They're essentially seeing with sound.
They really are painting a sonic picture of their surroundings. And we borrowed that idea for technology. Sonar, sound navigation, and ranging.
Used underwater mostly.
Primarily, yeah. Ships use it to detect submarines, map the seabed, find shipwrecks, even detect schools of fish or icebergs.
And it works the same way. Send out a pulse, time the echo.
Exactly the same principle. They send out pulses of ultrasonic sound frequencies too high for us to hear, and sensitive microphones listen for the echoes. The time delay tells them the distance using that d equals VT2 formula.
So v is the speed of sound in water, t is the round trip time.
You got it. And a specific application is echo depth sounding. Point the sonar beam straight down, time the echo from the seabed, and you calculate the depth of the ocean. It's how we map the ocean floor.
Incredible. The source also mentions radar as being similar.
Yeah, it's a nice comparison because radar radio detection and ranging uses the exact same echo principle, but instead of sound waves,
Uses radio waves or microwave.
right, electromagnetic waves, used for detecting aircraft, ships, weather systems, but the core physics of sending a wave and timing its reflection is identical.
Really shows how fundamental wave reflection is. And it's not just for navigation, is it? The medical field uses echoes too.
Oh, definitely. Ultrasonography, or just ultrasound as most people know it.
For seeing inside the body.
Exactly. High-frequency sound pulses are sent into the body, and they reflect differently off different tissues, organs, and fluids. The machine detects these returning echoes and builds up a real-time image.
Like for checking on a baby during pregnancy.
That's probably the best known use, but also for looking at the heart, that's called echocardiography, or examining other organs like the liver, kidneys, gallbladder, all non-invasively, just using sound echoes.
Amazing. The source also has some helpful numerical examples, doesn't it? Working through the calculations.
It does, yeah. Seeing the actual numbers for calculating distance from echo time in air versus water, for example, really helps cement the concepts, makes those formulas less abstract.
Definitely. Okay, so we've really covered reflection and echoes thoroughly. Let's shift focus now to the vibrations themselves. The source makes distinctions between natural, damped, and forced vibrations, and then resonance.
Right. Let's start with natural vibrations, sometimes called free vibrations. Imagine you pluck a guitar string or strike a tuning fork and then just let it vibrate on its own.
Okay, so you give it an initial push or disturbance, and then it does its own thing.
Exactly. It vibrates at its own inherent frequency, which we call its natural frequency. And that frequency depends entirely on the object's physical properties, its size, shape, mass, tension, what it's made of.
So every object has its own preferred way of vibrating. And ideally, in a perfect vacuum, would it just keep vibrating forever at the same amplitude?
Theoretically, yes. In that idealized scenario with absolutely no energy loss, the amplitude would stay constant. But, we don't live in a perfect vacuum.
Right. There's always air resistance or friction or something.
Precisely. And that leads us directly to damped vibrations.
Okay, so damped is just natural vibrations, but dying out.
Essentially, yes. In the real world, any vibrating object loses energy to its surroundings, usually due to resistive forces like air friction. This causes the amplitude of the vibration to gradually decrease over time.
So the swings get smaller and smaller.
Exactly. Think of pushing a kid on a swing and then letting them just swing. Each swing will be a little lower than the last until they eventually stop. That's damping.
And the energy is just lost. Turned into heat.
Mostly, yeah. It gets dissipated into the environment. The frequency of the damped vibration is usually very close to the natural frequency, maybe slightly lower, but the key thing is the decreasing amplitude.
Okay, so natural is the ideal, damped is the reality. What about forced vibrations then?
Forced vibrations are different. They happen when you continuously apply an external periodic force to an object, making it vibrate.
So it's not vibrating on its own anymore. It's being driven by something else.
Right. And crucially, the object is forced to vibrate at the frequency of the driving force, not necessarily at its own natural frequency.
Ah, okay. And how big are these forced vibrations? What determines the amplitude?
The amplitude depends heavily on how the driving frequency compares to the object's natural frequency. If the driving frequency is very different from the natural frequency, the object might vibrate a little, but the amplitude will likely be quite small.
But if the driving frequency gets close to the natural frequency,
then the amplitude of the forced vibration starts to increase. Consider holding a vibrating tuning fork and pressing its base against a table.
yeah, the sound gets louder.
Because the tuning fork is forcing the tabletop to vibrate at the tuning fork's frequency. The table itself might have very different natural frequencies, but it's being driven. The larger vibrating surface of the table moves more air, making the sound louder.
Okay, so forced vibrations are driven externally at the external frequency. Now, resonance. The source calls it a special case of forced vibration. What makes it special?
Resonance is what happens when the frequency of that external driving force exactly matches the natural frequency of the object being driven.
A perfect match.
A perfect match. When this happens, you get a really efficient transfer of energy from the driver to the object, and the object vibrates with a very large amplitude, much larger than it would for other driving frequencies.
Like pushing the swing analogy again. Pushing at just the right moment in each swing.
That's the perfect analogy. If you time your pushes to match the swing's natural back and forth rhythm, Even gentle pushes can build up a really big swing amplitude. That's resonance.
So it's all about that frequency match, causing a big energy transfer and a large amplitude. What limits the amplitude then? Does it just get infinitely large?
Well, not quite infinitely. It's limited by the damping factors we talked about, the friction or resistance in the system. If there were absolutely no damping, then theoretically, yes, the amplitude could grow without bound. But in reality, there's always some damping that dissipates energy and sets a limit.
Okay. The source gives some demonstrations, right? Like with tuning forks.
Yeah, the classic one is two identical tuning forks, each mounted on a hollow box called a sound box to amplify the sound. You place them near each other, strike one tuning fork to make it vibrate. The sound waves travel through the air to the second tuning fork.
And because the second fork has the exact same natural frequency.
It starts vibrating too, quite strongly in fact. It resonates with the incoming sound waves from the first fork. You can even stop the first fork and you'll hear the second one still ringing.
Wow. And the pendulum's example.
Also very clear. Imagine several pendulums of different lengths hanging from a single flexible string or rod. If you start one pendulum swinging, say a medium-length one, it makes the support string wobble slightly at its frequency. This little wobble acts as a driving force on all the other pendulums.
And only the pendulum with the same length as when you started swinging will really start swinging with a large amplitude.
Exactly. The others might wiggle a bit, but the one whose natural frequency, determined by its length, matches the driving frequency will resonate dramatically. It selectively picks up on that frequency.
And the air column resonance, like with a tube and a tuning fork.
Right. You hold a vibrating tuning fork over an open tube, maybe one where you can change the length of the air column inside, like by raising or lowering the water level in it. As you adjust the air column length, you're changing its natural frequency. When that natural frequency happens to match the tuning fork's frequency,
You get a sudden loud sound.
a very noticeable increase in loudness, yeah. The air column is resonating with the tuning fork.
The source gives some real-world examples, too, some quite dramatic.
It does. Things like machine parts rattling or vibrating excessively at certain engine speeds. That's often resonance, where the engine's vibration frequency matches the part's natural frequency.
Or the famous example of soldiers breaking step when crossing a bridge.
Yes. The concern there is that if the frequency of their synchronized marching matches a natural frequency of the bridge structure, the resonance could build up vibrations large enough to potentially damage or even collapse the bridge. It's a real phenomenon.
A sobering thought. But resonance isn't always bad, right? Musical instruments use it.
Oh, absolutely. It's crucial for musical instruments. The body of a guitar or violin, the soundboard of a piano, they are designed to resonate with the frequencies produced by the strings.
To amplify the sound.
Exactly. They amplify the sound, make it richer, and help project it. The air inside wind instruments also resonates.
Yeah, and radios and TVs, tuning them in.
That's resonance in electrical circuits. When you tune your radio, you're adjusting an electrical circuit, so its natural frequency of oscillation matches the frequency of the radio station you want to receive. This makes the circuit resonate, strongly amplifying that specific signal while ignoring others.
So resonance is powerful, can be useful, can be destructive. It all depends on matching that natural frequency.
Okay, let's shift gears one last time. Let's talk about how we actually perceive sound, the characteristics, loudness, pitch, and quality.
Right. And the source emphasizes the difference between our subjective perception and the objective physical properties of the sound wave that cause that perception.
Okay, let's start with loudness. That's just how strong a sound seems to us, right? That's the subjective part, yeah, our perception of strength or intensity.
And the objective physical thing behind it is intensity.
Intensity, yes.
Yeah.
Intensity is a measurable quantity. It's the amount of sound energy that flows through a unit area per unit time. Think of it like the power of the sound wave spread over an area, measured in watts per square meter.
So more intense sound wave generally means louder perceived sound, and intensity is linked to amplitude.
Correct. Generally, a larger amplitude wave carries more energy, so it has higher intensity, and we perceive it as louder. In fact, intensity is proportional to the square of the amplitude.
Square of the amplitude. So doubling the amplitude makes the intensity 4 times greater.
Precisely. But here's where the subjective part gets tricky. Our perception of loudness isn't directly proportional to intensity.
How so?
Well, for one thing, our ears aren't equally sensitive to all frequencies. A sound wave at, say, 3,000 hertz might sound much louder to us than a sound wave with the exact same intensity but at 100 hertz.
Ah, right. Yeah, we're most sensitive in the middle range, sort of where speech happens.
Generally, yes, around 1 kilohertz to 4 kilohertz. So loudness is subjective. It depends on the listener and the frequency, while intensity is the objective, measurable physical property.
Okay. What else affects how loud something sounds, besides amplitude and frequency sensitivity?
Several things. Distance from the source is a big one. Intensity drops off with distance, following an inverse square law, usually.
So further away sounds quieter. Makes sense.
Also, the surface area of the vibrating source. A bigger drum skin will generally sound louder than a smaller one hit with the same force.
Right. Moves more air.
The density of the medium matters too. And as we saw with resonance, the presence of other nearby objects that might vibrate in sympathy can amplify the sound, making it seem louder.
Now, the source mentions a logarithmic relationship between loudness and intensity. What's that about?
Yeah, that's key to understanding perceived loudness. Our senses, including hearing, tend to respond logarithmically to stimuli. This means that to perceive a sound as, say, twice as loud, you might need to increase the actual physical intensity by a factor of 10.
Wow, okay, so our perception kind of compresses the huge range of actual sound intensities.
Exactly. It allows us to handle an enormous range, from incredibly faint sounds to very powerful ones, without being overwhelmed. Mathematically, it's often expressed as loudness. L is proportional to the logarithm of intensity, I like L. Tell, AI like LKI.
And that's why we use decibels, because it's a logarithmic scale.
Precisely. The decibel dB scale directly reflects this logarithmic response of our ears. It compares the intensity of a sound, II, to a reference intensity, II, which is usually the threshold of human hearing. The formula is sound level in dB AII.
So a 10 dB increase means the intensity multiplied by 10.
Yes, and a 20 dB increase means intensity multiplied by 100. But perceptually, a 10 dB increase roughly corresponds to a doubling of perceived loudness.
Okay. The source has a table of dB levels, right? Like a whisper versus a jet engine.
It does, yeah. Useful for context. You see things like normal conversation around 60 dB, a vacuum cleaner, maybe 70, 80 dB, and things getting potentially damaging above 85 dB or painful around 120 dB.
Which brings us to noise pollution. That's just unwanted loud sound.
Essentially, yes. Sound that's disruptive, annoying, or potentially harmful due to its loudness or harshness. The source suggests a general safe limit up to about 80 dBs for continuous exposure.
Okay, let's move to the next characteristic. Pitch, how high or low a sound is.
That's our subjective perception, pitch.
And the objective property behind it is?
Frequency. Pitch is almost entirely determined by the frequency of the sound wave.
Higher frequency, higher pitch.
Exactly. Higher frequency means more vibrations per second, which our brain interprets as a higher or shriller pitch. Lower frequency, fewer vibrations per second, lower pitch.
Like the difference between a piccolo and a tuba. Or thin guitar strings versus thick ones.
Perfect examples. Or think about tightening a guitar string. You increase the tension, which makes it vibrate faster, increasing the frequency and thus raising the pitch.
The source also mentions filling a pitcher with water while tapping it.
Yeah, or listening to the sound as you pour water into it. The length of the air column above the water changes, which changes the resonant frequency, and you hear the pitch change.
So again, subjective perception, directly linked to an objective measure, frequency. Simple enough. What about the third one then? Quality or timbre?
Quality or timbre. This is maybe the most interesting one. It's what lets us tell the difference between, say, a violin and a piano playing the exact same note, same pitch, at the exact same loudness.
They just sound different. They have a different character.
Precisely. That character, that unique sonic fingerprint, is its quality or timbre.
And what determines that physically?
It's determined by the waveform of the sound.
The waveform, you mean the actual shape of the wave pattern?
Exactly. A pure tone, like from an ideal tuning fork, has a very simple, smooth, sinusoidal waveform. It consists of just one frequency, the fundamental frequency. But most sounds, especially for musical instruments or voices, are much more complex.
How so?
They contain the fundamental frequency, which determines the pitch we hear, but they also contain a whole series of additional higher frequencies called overtones or harmonics.
So multiple frequencies are present at the same time.
Yes, and it's the specific combination which overtones are present and their relative intensities or loudness compared to the fundamental that creates the overall complex waveform.
And different instruments produce different combinations of these overtones.
Exactly. A flute might have a relatively simple set of overtones, giving it a purer sound. A trumpet might have a rich, complex set of strong overtones, giving it a brassy sound. A violin's waveform is different again.
So the unique recipe of fundamental plus overtones gives each instrument or each voice its characteristic quality.
You've got it. That's why you can recognize a friend's voice on the phone or tell instantly if it's a guitar or a saxophone playing, even if they play the same note at the same volume. It's all down to the waveform, shaped by those overtones.
Fascinating. The source has a summary table for this too, right? Connecting the subjective characteristics to the objective properties.
Yes, it neatly lays it out. Loudness depends mainly on amplitude and intensity. Pitch depends mainly on frequency. Quality depends mainly on the waveform, the mix of fundamental and overtones.
Very clear. Finally, the source makes a distinction between music and noise. Is there an objective line there?
Well, it tries to draw one, but it admits it's also quite subjective. Generally, music is described as pleasant, often produced by regular, periodic vibrations. Think smooth, repeating waveforms, usually at moderate sound levels.
Okay. Regular, periodic, pleasant, and noise.
Noise is typically described as unpleasant, harsh, jarring, often produced by irregular, non-periodic disturbances. Think jagged, unpredictable waveforms, often associated with loud sounds, maybe above that 120 dBp pain threshold.
Like a jackhammer versus a melody.
Right. But as the source notes, the line can blur. What's music to one person might be noise to another. Think of certain genres of modern music, perhaps? Or even just a poorly played instrument could sound like noise.
So there are typical physical differences in the waveforms and regularity, but our perception and preference play a huge role.
Absolutely. The source provides a comparison table, but acknowledges the subjective element is always there. And again, there are some good numerical examples showing how wave properties relate to these perceived characteristics.
Well, we have certainly covered a lot of ground today, really diving deep into the physics of sound.
We really have. From how sound waves are made and travel, through reflection, echoes, the different kinds of vibrations, resonance, all the way to how we perceive loudness, pitch, and quality.
Yeah, and for me, some real aha moments were definitely understanding that precise 0.1 second timing needed for an echo.
The persistence of hearing.
And seeing how resonance works, that perfect frequency match causing amplification. And also really grasping that subjective versus objective split for loudness, pitch, and quality. It's not always a direct one-to-one relationship between the physics and our experience.
Absolutely. Understanding these principles, I think, just gives you a much richer appreciation for everything you hear from, birdsong to a concert hall to the technology that relies on these principles.
Definitely. So for our final thought to resonate with you, consider this. We've seen how understanding sound waves and resonance led to things like ultrasound imaging and radio communication.
Incredible technologies, really.
So what other potential breakthroughs might be unlocked as we get an even deeper understanding of the science of sound? What else could we hear or do with sound waves in the future?
That's a great question to ponder. Definitely something to keep an ear out for.
Indeed. Thanks for diving deep with us today.